Okay, welcome to our Chapter 12 video for our physics class, where we are going to be talking about sound. And this is a really good way to pick up after the last chapter where we talked about waves in general and the way waves can transmit energy and travel through various media. Because sound is just an example of a specific example of waves. Sound travels through various materials, and the material that the sound waves are traveling through affect their velocity or speed. And so we typically tend to think of sound traveling through air because we think of sound as what we humans hear, and we humans spend most of our time living in air. And so the speed of sound or velocity of sound waves in room temperature air, which would be about 20 degrees Celsius or 70 degrees Fahrenheit, is 343 meters per second. But you can see here in this chart that at 0 degrees Celsius, at a colder temperature, the speed of sound is less. We can also see here that, let's see, what's the highest number on here? 5,100 maybe? Yeah, it looks like that's the highest number. So aluminum. So sound can travel through solids. If you think of like banging on a long pipe or something, that sound of banging on it with a hammer will travel down the length of the pipe through the solid material faster than it will through the air. So sound can travel through solids. It, of course, can travel through liquids. If you've ever been swimming underwater, you can still hear things. So don't just think that sound can travel through air. Sound can travel through a lot of things. And also don't think that there's just one single speed of sound. Although this is the most common speed of sound that we will be using, it depends on temperature and the material that the sound is traveling through. So there can be lots of different speeds of sound. In fact, we have a formula here for the speed of sound in air specifically. The velocity is going to be 331. That was the temperature at 0, or the speed at 0 degrees Celsius. But then we add to it 0.6 T, where T is the temperature in degrees Celsius. So using this formula, we should be able to calculate the speed of sound in any temperature air. All right, so I've thrown this slide in here as a reminder that sound does need a material to travel through. Alien is one of my favorite sci-fi horror films, and its tagline was, "In space, no one can hear you scream." That tagline has a double meaning. On the one hand, it was about the crew of a spaceship that were isolated far in deep space, and there was no one around to help them. But in a literal physical sense, space is a vacuum. There is no air in outer space. Therefore, sound cannot travel through outer space. So think of every science fiction movie you've ever seen in which there are explosions that are making a loud boom. That is physically impossible. You cannot hear things in outer space because it's a vacuum, and there's no material for the sound waves to travel through. So sound has several different characteristics that we can talk about. The first is loudness. So just think of turning up or down the volume on a stereo or your whatever audio device you're listening to. That is changing the loudness. it's related to, but not exactly the same as the intensity of a sound wave. And we'll talk about that a little bit more in a few slides from here. There's also pitch. So sounds can have a high pitch or a low pitch. It can sound, musical notes. Different notes are based on different pitches, and that is affected by the frequency of the sound wave. So by changing the frequency, we can change the audible pitch of a sound. Humans can hear sounds between about 20 hertz, which is very low pitch. That's a very low frequency, all the way up to about 20,000 hertz, which is very, very high frequency. And so I've got a video. I'm not going to include it here in the PowerPoint. I'll try to post it on the Blackboard, which is it's supposed to illustrate how really high-pitched sounds with really high frequency can be more easily heard by younger people. The older you get, the more damage is done to your ears, and the less capable you are of hearing these high-pitched sounds. Unfortunately, the video I have comes from YouTube, and YouTube compresses sounds to keep the file sizes relatively small. So it kind of chops off some of the highest frequency sounds. And so if you listen to the video and you can't hear some of the higher frequency sounds, it's not because you have experienced any damage to your ears. It's just because YouTube doesn't actually play it doesn't play sounds that are really high frequency. But it's still a good illustration of some of the other frequencies that are within what YouTube will play. You can take a listen to that. So look for that on Blackboard. So that leads us to this idea of an ultrasound. An ultrasound essentially is just a there we go. It's just any sound that is above the range of human hearing. So anything above 20,000 hertz, we can't hear that as humans. And infrasound refers to any frequency that is lower than what humans can hear, anything below 20 hertz. So this example problem is a bit dated. I don't know that this technology is still in use, but if you have an older autofocusing camera, for a time, the way that they focused themselves was by detecting the distance to the object being photographed with an ultrasonic sound pulse. And it would emit a tone. That tone would travel to the object being photographed, and then it would bounce back to the camera. The camera would then detect the length of time that it took for that sound wave to travel, and based on that time, it would calculate how far away the object was, and then adjust the lens to focus on that object that is that distance away. So in this example problem, we are going to attempt to calculate what that travel time is for the pulse to reach an object that is first 1 meter away and then 20 meters away. Okay, so first of all, we have to make the assumption that this is taking place at room temperature, approximately 20 degrees Celsius. And based on that assumption, then, we can look up the speed of sound on the chart I had on the previous earlier slide, and see that the speed of sound in room temperature air is 343 meters per second. So we just need to use a simple equation that velocity is displacement over time. And so if we then solve for velocity, or no, I'm sorry, solve for the displacement is equal to the velocity times time. So if our velocity of sound in room temperature air is 343 meters per second, we then just need to multiply that by, oh wait a minute, we're wanting to find time. So I should have solved this equation for time. So that goes there, and time is equal to displacement over velocity. So let's just scribble this out and start again. Our displacement. So here's a little thing here for this problem that we have to be aware of. Let's say here's our camera, and here's the object we're taking a picture of, little smiley face guy. So when it's 1 meter away, the distance we're talking about is not just 1 meter, because that sound wave has to travel to the object and then travel all the way back to the camera. So the distance is actually 2 meters divided by 343 meters per second. So that will give us our time, which is what we're looking for, and that's equal to 0.0058 seconds. Yes, so I should have actually made this 2.0 because of the problem statement said it was 1.0 meters away, I believe. Let's go back to that. Yes, 1.0. So I want to make an emphasis to use and demonstrate proper significant figures because that still seems to be an issue on both homeworks and tests, not using the appropriate significant figures. So we should have two significant figures in this answer, 0.0058. And then for part B, we were talking about something that was 20 meters away. So again, it's got to travel 20 meters to the object being photographed, 20 meters back. That's a total of 40 meters. So the time it's going to take for that to happen is going to be the distance divided by velocity. The distance is 40 meters divided by same velocity, 343 meters per second, and that is going to be equal to 0.12 seconds. So based on the varying times here, whether it takes 0.0058 or 0.12, the camera then is able to determine how far away the object is and then focus on that object. I think this is a good stopping point. I'll resume in the next video.